so far, when we are doing cost-benefit analysis, we have been assuming that we know the benefits, know the costs, particularly in the future, for sure. However, this is not the case, particularly if the project we want to assess involves many years. We don't know future for sure. For example, we don't know what will the benefit be next year. So now we are faced with risks. We need to account for such risks in our cost-benefit analysis. But before that, what do we mean by risks? So risks is where subjective probabilities can be assigned to possible outcomes. Okay, so like tomorrow's weather, it could be a sunshine day, it could be a rainy day, it could be a cloudy day. We don't know for sure, but we are able to assign probabilities, for example, from the past weather records. Say we estimate that tomorrow, the probability of having a sunshine day tomorrow is 70%. The probability of having a cloudy day is 20%. The probability of having a rainy day is 10%. Sometimes we also call this uncertainty. Okay, but rigorously speaking, there's a difference between risks and uncertainties. Uncertainty is something that you cannot assign probabilities, which means you cannot insure against these items. However, we will not distinguish between them and we'll just use them interchangeably. Okay, so we know what risk is now. Then how do we measure it? Let's look at an examples here. Say my project depends on weather. Tomorrow's weather. It could be sunny day, could be cloudy, and could be rainy. Okay. And I'm able to estimate probability of this. So sunny day, the probability 0.7, cloudy day is 0.2, rainy day is 10% chance. And my project depends on this. If it is sunny days, the NPV of my project is say 10 million. So this the unit of NPV is say $1 million. So it's 10. If it is cloudy days, then it's 2. If it is rainy days, I'm going to make huge loss. So it's -5. Okay. Right. Then one thing. Okay, so now I'm faced with this risk, uncertainty about the future. One thing that I will care about is, on average, what my NPV is going to be. Okay, let's calculate average. So first, let's weight each possible outcome by its probability. So C2 times B2. And do it for all other possible outcomes. Sum them up. So mean or expected NPV. This is expected NPV. Sum up. So on average, I expect to have a 6.9 million NPVs. Okay, in addition to this mean I also want to measure risks. How can we measure risks? Okay, let's do this. Let's first calculate each possible outcome's deviation from its mean. Okay, so for the first outcomes is C2 minus D5. I'm using dollar signs to fix the reference. So that's deviation of first outcome from this mean. 3, let me just, okay, 3.1. Similarly, do it for second outcome and third outcome. Second outcome is $4.9 million below the average. Third outcome is $11.9 million below the average. And so now you want to note that deviation from mean, you want to pay attention to the unit is $1 million. Okay, then I'll be quite, so now we calculate the deviation from mean. Then I'll be quite tempted to just sum up these deviations, and let's do it, see how it goes. So it's negative $13.7 million. Unfortunately, so here you should observe that we can have positive deviation and negative deviations. If we sum positive deviation with negative deviations, then they cancel each other out. So this is not a good idea to sum them up. Okay. So let's get rid of the negative sign. So let's compute square deviation, which is E2 squared So now you want to pay attention to the unit here. So the unit of deviation is $1 million. So I squared, so it's $1 million squared. Okay, so $9.61 million squared. And now the issue about this $1 million squares that is actually not intuitive. Okay, so let's handle this in a moment. Okay, I calculate the squared deviation. Let me weight this squared deviation by its probability. So F2 times its probability, so B2 then sum them up, and we call this variance. So sum them up. So this $25.69 million squared. Okay, so let me write it out. Squared. Okay, that's the unit of this variance. But that's not intuitive, not easy for us to understand. This square root back. Okay, so we call it standard deviation. So which is equal to G5 square root G5. So it's 5.06853. Now we have $1 million unit. Okay, and we using this standard deviations to measure risks. So two statistics here. One is mean. We use mean average to measure how concentrated our MPV is going to go, our risky MPV is going to be. In my example here, it is $6.9 million. To measure risk, we use standard deviations, so which is computed from variance, which in turn is the weighted sum of weighted squared deviation. And the higher standard deviation, the higher risks associated with the project. And in my working examples here, the MPV, the possible MPVs, the MPVs only have 3 possible outcomes: sunny day outcomes, cloudy day outcomes, rainy day outcomes. So now if we say that my MPV is a discrete random variables, okay. Sometimes we can have continuous random variables, okay. So in such cases, the expected MPV will be equal to sum of MPV. This MPV has a distribution function gx, okay. I'm going to use x, big X, to denote MPV, okay. So it's x gx dx, okay. Integrate over all suppose all possible range of the all possible realization of x, and this is called ex. Okay, so that's mean. Variance can be computed as each possible realization of x MPV, each possible realization of MPV calculus is deviation from its mean, square it, weighted by its probability. You can think that this PDF probability density function, loosely you can think it as a probability, then sum them up. So this integral signs loosely you can think that it's a sum. It's a sum. All right, so that's how we measure. That's how we measure the risks. So now we have measured the risks. So we want to make decision. Given that we have expected MPV and the risks associated with these projects. So should we accept or reject the project? So now the decision making somewhat depends on risk attitude. So risk attitude vary from neutral, risk averse, or risk seeking. So risk neutral, it is sometimes asserted that government should be risk neutral. That is, they should make decisions based on expected MPV without considering the risks. Okay, in the case here, we can suppose we have 2 projects. This is project A, this is project B, and we computed the distribution of the MPVs, and the curve here is the probability density function of the MPVs of project A and B. We can see that both curves is symmetric around 2. So expected value of MPV for both projects is the same. Is $2 million. But for project B, clearly we can see it's more spreaded. In contrast, project A is tighter. So the variance of MPV of project A is smaller than variance or standard deviation of project B. Okay, so if we are risk neutral, then we are going to ignore the risks. We are going to say that, okay, in these cases, project A is actually the same as project B. So a risk neutral investors will make decisions on the expected value, the average of the potential returns. And here's an examples. The justification for risk-neutral approach for government projects, which might or may not be valid, we have the following reasons. First, any one project is likely to involve a small amount of the government's or society's resources. So damages from loss will be small. In such cases, it may be a good idea to be risk neutral. Second justification. Risks borne by projects are likely to be independent overall. One project is independent of another. So the government can have a diverse portfolios. So the collective unsystematic risks will be diversified away. Second justification. However, the systematic risk cannot be diversified away. Third justification. The risk is pooled between a large number of taxpayers. And some taxpayers will be risk averse, while the others will be risk seeking or risk neutral. In such cases, the government should reflect the public's values. So the government pools all this risk, all taxpayers' risk attitudes, and maybe in the end should be a risk neutral. The fourth justification. National development has been built on governments undertaking risky projects, which private enterprises will not undertake. So essentially, we are saying that if the governments do not undertake risky projects, then nobody will do it, and we end up in having no project at all. Okay, despite this argument, it is generally argued that governments should be risk averse, like most of the public. Okay, that's one attitude, risk neutral. Second possible attitude is risk averse. Most people are considered to be risk averse. That is, they try to avoid risk. Will prefer project A, which has a low risk, compared with project B. Or in other words, they will only accept higher risks if it is compensated for by a higher expected returns. So they will discount risky projects. And some investors or gamblers, they are risk seeker. That is, they seek risky projects because for risky projects, there's a higher chance of getting higher returns than the less risky project. Okay, so suppose I have two projects, as I said before, as we see it in the diagram, project A and B. So expected NPV was 2 million. And associated risks, which is standard deviation. So project A is $1 million. Project B is $4 million. Okay, then decision making is, if it's risk neutral, then A is the same as B. If it's risks averse, then you are going to prefer project A. So A is better than B. If it is risk seeking, then you are going to prefer B over A. Okay, let's measurement of risks and decision making with risks.